In previous lectures, we have seen two different ways of characterizing analytic functions. You can either say that a function is analytic if it's complex differentiable, or you can say that it's analytic if it's the integration of the function is locally path independent. In this lecture, we will consider a third way of characterizing analytic functions by power series expansion. So let's consider first a power series like this. If we assume that the radius of convergence of this power series is positive, then inside the domain of convergence, this will define an analytic function. In fact, by the theory of power series, you can easily see that you can differentiate this power series, and the derivative will simply be the, so to speak, formal derivative here now. You can just take the derivative of this polynomial inside here. And this again defines a power series which is convergent within the same disk as the original one, and this proves that it's complex differentiable, and hence it's analytic. But what's interesting is that it's also true in the other way around. As soon as you have an analytic function in the sense that it's complex differentiable, or if the integration is path independent, then you can always express it locally in terms of a convergent power series. So this is the first object for today. Suppose that we have a circle here around a point Z0, where we know that the function is analytic. Actually, we can assume that it's analytic in some open neighborhood of this closed disk then. Then we know that we have the Cauchy formula. So we know that we can write f of z as 1 over 2 pi I times the integral around the boundary here. Let's call the boundary CR here now for the moment. Of f of w divided by w minus z dw. This is the Cauchy formula, which we have proved earlier then. And from this, we will now derive the power series expansion. So the computation goes as follows. The first trick here is to add and subtract the point Z0 in the denominator. So we write it, that's W minus Z0 minus Z0 minus Z, like this, and dW also. So this doesn't change anything because we have, Z and Z0 like that. Then we have subtracted Z0 and we have added it again at the end. And the next step now is that we extract from the denominator this factor W minus Z0. Which gives then 1 over W minus Z0. And then we have still here f of W. And over here we get 1 minus Z minus Z0 divided by W minus Z0. And then we also have dW. And the point is now that whenever Z lies within this disk, then since W is always on the boundary of the disk, then the absolute value of the numerator here will be smaller than the absolute value of the denominator, which means that this expression here now, 1 divided by 1 minus Z naught divided by W minus Z naught like this, can be expanded in a convergent power series. It's actually a convergent geometric series then. So we can write it as some k goes from 0 to infinity of Z minus Z naught divided by W minus Z naught to the power k, you know. And actually this series then converge uniformly on every compact subset of the open disk, you know. And so if we introduce this expression here in our integral, then we arrive at following expression then. So it will be the integral of, and then we have first let's write it as f of w, and then we have this sum here, k goes from 0 to infinity of Z minus Z naught to the power k, and then we also have W minus Z naught here to the power k in the denominator. But since we have this extra factor here, you can put k plus 1 there, and then dw. And now, since this is a uniformly convergent series for any fixed Z inside the disk, one can actually integrate this series term by term, which is something that is proved in the theory of power series then. And then in this context, this means that we can actually move the summation outside here. So we get sum k goes from 0 to infinity of 1 over 2 pi I, and then we have the integral CR over the circle CR, and then we have f of W divided by W minus Z naught to the power k plus 1 and dw. And then at the end here we put this factor, which is of course independent of the variable of integration, so we can put it outside the integral. So now we see that we have arrived at a formula of this type. We have sum k goes from 0 to infinity of a k Z minus Z naught to the power k, where this coefficient ak is actually given by this integral here now. So we have arrived at a power series expansion for the function f. Of course, there are a few technical details to check that this has positive radius of convergence and that you can really do this interchange of integration and summation and so on. But all that is easily done using the Cauchy estimates for the derivatives of the or you don't even need the Cauchy estimates, but you can simply estimate this this integral here and use the theory of power series then. So let's consider a few examples then of power series. First of all, of course, we have the exponential function. Oh, sorry. In most approaches to complex analysis, this is really the definition of the exponential function then. But of course, whatever definition you use, once you have the definition, this will also be the power series expansion of that function. And of course, you have similar expansions for example, the sine function and the cosine function and so on. You also have a power series expansion for the logarithm function. So let's suppose that we have considered the principal branch of the logarithm function at the point 1 over at the point 1 plus z. And then, of course, this is given by the usual power Taylor series. Then. So you will get some k goes from 1 to infinity of minus 1 to the power k plus 1 divided by k times z to the power k. You can then observe that this power series, of course, has infinite radius of convergence. It converges for whatever complex number z you insert here. Here, on the other hand, you see that this power series will only converge as long as essentially when the absolute value of z is less than 1. And it's not difficult to see that this is the way it must be, because if you insert, for example, the value minus 1 here, you will get to a point where the logarithm function will definitely be singular, and you cannot hope to represent it by a infinitely differentiable power series at that point. In this context, you can also then consider the arctangent function. So let's take the principal branch of that also then. Well, then you can write it as some k goes from 1 to infinity of 1 minus 1 to the power k plus 1 divided by 2k minus 1 times z to the power 2k minus 1. This is also exactly the usual power series, but in a complex setting then. In this case, you also see that the radius of convergence is 1 actually here, because once absolute value of z is less than 1, then this essentially converges geometrically. But when the absolute value of z is larger than 1, this will not even go to, the terms will not even tend to 0. But in this case, the reason is less obvious then, because the arctangent function, as long as you consider the real theory, the real variable theory, then this is infinitely differentiable along the whole real axis. So you don't really see the singularity. But once you turn to the complex situation, then it turns out that this function will have singularities at the point I and minus I. So if you study this as a complex function, or this, then you see that the radius of convergence can definitely not be larger than 1, because then, for the same reason as you had up here, you will approach points where the function is singular. Okay, so finally now I will consider an application of theory of power series then. Recall that the Fibonacci numbers are defined in the following way. You put the first two equal to 1, and then every consecutive Fibonacci number is defined as the sum of the two previous ones, like this. So if you compute these numbers, you get first you have 1, 1, the next one will be 2, and then you should sum these, you get 3, and then you sum these, you get 5 and 8, and so on. And this is a very interesting and common sequence of numbers that occurs in all kinds of applications. But it's not quite trivial to find a formula for them. So here you have recursive definition, but really you would want a formula which expresses the Fibonacci numbers as a function of k. And this can now be done using the theory of power series expansion then. So let me first note here now that if we introduce the analytic function, which is then the power series, some k goes from 0 to infinity of ak z to the power k, where the ak's now are the Fibonacci numbers. Then this will define an analytic function. Actually, to do this, you have to do some elementary estimates of the growth of these Fibonacci numbers. But it's well known that the size of these numbers, they grow essentially like at most 7/4 to the power k. Then. And this shows that this has a positive radius on convergence then. And now you can use this relation here now to find an equation for f of z. In fact, if you, it turns out then that f of z is equal to 1 plus z times f of z plus z square times f of z. Well, why is this? Well, essentially you just have to compare the coefficients in the power series expansion on the left-hand side and on the right-hand side. So the constant term here is of course just 1 because it's the first term in this series, and also these contain no constant term, so you get a 1 here also. And similarly, the second term here will be z, because that's really the term k equal to 1 here on this side. And this does not interfere, and this does not interfere. And here the first term will be z times the first term in this expansion, which is 1 then. So you get z on both sides. And for higher ordered terms, you just see that because of this equation then, the kth term will agree on both sides here now. So here the kth term will have coefficient ak, and here it will be, since you multiply by z, you should look at the coefficients of 1 degree lower. So here it will be ak minus 1, and here for the same reason it will be ak minus 2. So because of this relation, you also get this relation. And now you can solve for f. So if you just collect all these terms which contain f on the left-hand side, you see that you get 1 minus z square. And then there's only this 1 left here now. And then you can divide this equation now by the factor 1 minus z square. And you get an explicit formula for f. So once we have this explicit formula for f, we can use it to deduce an explicit formula for also for the Fibonacci numbers. So what you do is simply that you compute the power series expansion, and the first step to do that is to use the partial fraction decomposition on this rational function. So to do that, you first solve the equation where you put the denominator equal to 0. And it turns out that the two roots will be gamma 1, which is square root of 5 minus 1 divided by 2, and the second root will be minus square root of 5 plus 1 divided by 2. So this is actually the famous golden ratio equation, and these are the two roots then. And once you have this, you can compute the partial fraction decomposition, which looks like this. And when we have this now, it's quite easy to compute the power series expansion, because both these terms can be expanded just by a simple geometric series then. So if we take 1 over gamma 1 minus z, then we can write it as 1 over gamma 1 times 1 divided by 1 minus z divided by gamma 1. And this, by the power series expansion, will become sum k goes from 0 to infinity of z divided by gamma 1. And here you have power k and power k. And so if you multiply this in here, you get z to the k divided by gamma 1 to the power k plus 1. And of course, similarly, you have for the second term the expansion then which looks like this. And so if we now insert these two series in here, you get a power series expansion for f, and then we can simply read off what the different coefficients in that series, what they look like. So we just take the kth coefficient, which is ak, which is the kth Fibonacci number. It will then be 1 over square root of 5 times the kth coefficient in this series, which is then, according to this formula, 1 over gamma 1 to the power k plus 1. And then you get minus 1 over square root of 5 here. And similarly, when you insert this series here, you get the coefficient gamma 2 to the power k plus 1. So this is really an explicit formula for the kth Fibonacci number. So if you want it still more explicit, you can now insert the values here of gamma 1 and gamma 2, and then you get the following expression here now. So you get 1 over so you get 1 plus square root of 5 divided by 2 to the power k plus 1 minus 1 minus square root of 5 divided by 2 to the power k plus 1, like this. Actually, here you have used the formula for inverting these roots. You can observe that if you multiply gamma 1 and gamma 2 with each other, you will get minus 1, which slightly simplifies this expression then. But still, you get a rather complicated polynomial in where you insert square root of 5. But as it turns out then, since the Fibonacci numbers, they are all integers, all these square root of 5 will cancel out here when you actually do the computation. So this, although we can't see it directly, this is really an integer.